So I thought I'd do some examples about how you put all this together. How do you use that P over Q rule, Descartes' rule of signs, and synthetic division or substitution to factor a polynomial? Because quadratics are easy. What happens when it's something else? So this is what we're going to do. So here's a problem I have, and they want me to factor this or solve it or do something along those lines. So first off, let's figure out the possible solutions, the possible rational roots. Well, I know I'm going to take the P number and the Q number and factor them. Remember to go plus or minus. So I could do plus or minus 1 for the P, and then 10, and then plus or minus 2 and 5, and plus or minus 10. And then that's all over the Q number. Remember, the Q number is the number in front of the leading coefficient, or it's the leading coefficient in front of the leading term. So that's going to be plus or minus 1. So basically, I've only got to test these 8 pairs of numbers, because all the 1 does is change the signs, and the signs are already changing. So now, how can we trim this down? I don't want to do all that work. So Descartes' rule of sign tells me, well, if I'm looking for the positive rational roots, or the possible rational roots, I'm counting no sign change, there's a sign change, and there's another sign change. So that tells me there could be 2 positive rational roots, or there could be 0 rational roots, and in which case there could be 1, based on what we know now, there could be 2 rational roots, and there can't be 1 complex root because they got to come in pairs. So it could be, if there's 0 positive rational roots, here, let me write that as a positive rational roots. In that case, there would be 2 complex roots. And it looks like there's going to be something else with the negative roots. So let's do f of negative x and see what's happening to find the possible negative roots. So let's see, that would become negative x cubed. But when I drop negative x into x squared, that stays positive. I mean, that becomes positive. So that 2 doesn't change signs. Negative x times negative 13 turns out to positive 13x. And then, of course, the 10 doesn't change. So I'm only seeing 1 sign change here. So that tells me there's 1 negative rational root. So that can't reduce that by 2. So looks like there is definitely one negative rational root, and there could either be 2 complex or 2 rational. That'll make a total of 3 using the fundamental law of algebra, fundamental theorem of algebra. Okay, so now let's find them. So I know, since there's only 1 negative root, 1 negative rational root, I'm only going to test 1, 2, negative 1, negative 2, negative 5, negative 10 and see what happens. So what do we start with? Well, I see that these numbers aren't too large in the middle, so I'm almost thinking that 10 might not be a good choice. Let's try 1, see if negative 1 works. Remember, I'm testing negative numbers, so 1, 2, negative 13, and 10. So that's negative 1, leaves me 1. That's negative 1, that's negative 12. That's positive 12, well, that's 22. That's dead. That doesn't work. So I decided to test negative 2. So bring down the one, that's negative 2, that's 0, that's 0, that's negative 13. That's going to be positive 26. That's done. I'm not even going to finish. Bring down the 1, that gives me negative 5. That's negative 3. That gives me positive 15. So that's 2, that's negative 10. 10 minus 10 is 0. So that's one of the roots. X equals negative 5, which means that one of the factors is x plus 5. So now I can use, I know I've got a quadratic, x squared minus 3x plus 2. And that factors to x minus 2, x minus 1. So x has to equal 2, x has to equal 1. So here's what I'm seeing. I am seeing 2 positive rational roots. I'm seeing 1 negative rational root. And so we know that confirms what Descartes' rule of signs told us. So we need to write finally a factored polynomial for all this. So I know that f of x has to equal x minus 2 times x minus 1 and x plus 5. Now something you learn in pre-calc and in some algebra 2 classes, that these are the places at -5, +2, +1 where this polynomial crosses the x-axis. We'll also learn about ending behavior, how these polynomials act. So it's pretty interesting the way it all comes together. So I'm going to do another one and have you help me through it. So here's another 4th degree polynomial. I know there's going to be 4 zeros. I don't know whether they're positive or negative or complex. So that's what we're going to do. We're going to find. So let's see. Let's start with that P over Q thing. So I'm going to let you. Not going to say anything. I want you to stop the video. I want you to write down what do you think the possible rational roots are. Not, this is just doing the P over Q thing. Or remember, this is the P value and the 1 in front of that is the Q. So stop the video, try it, come on back and watch. So I'm going to, let's see, 30 is plus or minus 1 and plus or minus 30. That's going to be plus or minus 2 and plus or minus 15. Plus or minus 3, plus or minus 10, and then I got 5 and 6, and I think that's all the choices. Let's put some commas between those so I help keep myself straight here. And then for 1, well, 1's easy. It's just plus or minus 1 for the Q. So what one do we try? Well, this is where Descartes' rule of signs will help us. So why don't you apply Descartes' rule of signs, see what you come up with, come back and watch mine, and we'll compare and keep rolling. So to apply Descartes' rule of signs, I'm seeing no sign change, no sign change, no sign change, no sign change. That's telling me there's going to be 0 positive rational roots. So now let's drop in f of negative x and find out what happens. Well, negative x to the 4th power is still positive. Negative x to the 3rd power turns out negative, so that makes negative 11x cubed. Sign doesn't change for negative x squared. Sign does change for the 61, so negative 61x, and of course the 30 doesn't change. So we're seeing 1, 2, 3, 4 sign changes. So it could be that I'm going to have 4 negative rational roots, or I could have 2 negative rational roots along with 2 complex roots, or I could have 0 negative rational roots and 4 complex roots. So now we're going to go back and hopefully we're going to get at least 2. We'll have to use those P over Q ones. We know they're all going to be negative, so that kind of eliminates half of our choices. So you haven't seen all this work I've done. I've tried negative 10, I tried negative 6, neither of those worked. I decided to try negative 5, and surprisingly enough, it does work. So I bring down the 1, I get negative 5, that gives me 6, that's negative 30, that's 11, that's negative 55, which is 6, negative 30, that's 0. So that leaves me, now this is a 3rd degree polynomial, right? It leaves me 1x cubed plus 6x squared plus 11x plus 6. I got to try another problem. So I'm going to go back, play around with some of these roots. I've already used negative 5, so maybe I should try negative 6 now, or negative 2. I don't know. I'm going to check it out and see. You should too, and then come back and see how I did and compare it to what you did. Well, I tried negative 2. It was a lucky guess. It was the first one I did, and it worked out to be 0. So that leaves me this quadratic of x squared plus 4x plus 3 equals 0. Well, I'm seeing right now that that's going to factor to x plus 3 to x and x plus 1. That'll give me 4x in the middle. So that tells me -3 and -1 are both solutions. So I've got 4 negative solutions. -5, -2, -3, -1. And this polynomial would factor to these 4 factors. And there also are zeros. I know the zeros are -2, -5, -2, -3, and -1. And that's consistent with what Descartes' rule of signs showed us. So showing us they were going to be either 4 negative rational roots or 2 negative rational roots and 2 complex, or it could be 4 complex. In this case, we got the 4 rational. So I hope that helps you put this all together. Why we can use Descartes' rule of signs, and it's just one way to do it. Okay, hope that helps. Now suppose I have to make up a polynomial that's got 2. Let's make this up. Let's suppose the conditions it has to have 1 positive rational root, and let's suppose it has to have 1 negative rational root, and then 2 complex roots. All right, so let's make this up. Let's see, 1 positive, so let's pretend that's one of our numbers, x minus 1. Actually, let's make it not be 1. Let's be x minus 4. And then the other one, I could have a negative rational root, so how about x plus 2? And then to get the 2 complex roots, what you've got to remember is that the complex roots come from taking the square root of a negative number. So if I think about x being plus or minus the square root of, say, 9i, I'm sorry, not -9, not -9i. That would be plus or minus 3i, right? So if we go backwards, that's the square root of -9. If we go backwards further still and square both sides, that gives me x squared equals -9. So my factor would be x squared plus 9. So here's my factors for my polynomial. If I expand those all out, I won't make you watch that. So when I FOILed that, what did I get? Let's see, I got x to the 4th minus 2x cubed plus x squared plus 8x plus, oh sorry, it's minus 18x. Minus 72. So now we're going to pretend we didn't know where this came from and apply everything we know up to this point and try to come up with these factors and zeros. So the first thing we're going to do is we're going to try to find all the possible factors using that P over Q trick. And once you stop the video, you try it, then you come back and compare it to mine. So what I'm seeing is the 72, so I got to come up with -72. So plus or minus 1, plus or minus 72. Then it can be plus or minus 2 and plus or minus 36 and plus or minus 3, which is plus or minus 24. And then plus or minus 4 and plus or minus what is that, 18? And then plus or minus 5 won't go in, 6 will. Plus or minus 6, plus or minus 12. And then I think I got plus or minus 8 and plus or minus 9. All over plus or minus 1, because the Q is 1. So let's see, so I've got a lot of possibilities. I don't want to test them all. I think we're going to use Descartes' rule of signs to narrow some of these out. So why don't you try it, come back and watch what I do, and we can compare. So I'm seeing, let's see, to find the positive rationals. I'm seeing 1 sign change, 2 sign changes, 3 sign changes, and that's not a sign change. So there could be 3 positive rational roots, and, well, there can't be any complex roots because there's only 4 total. Or there could be 2 positive rational roots, I'm sorry, 1 We're taking away 2, aren't we? So 3 minus 2 is 1. 1 positive rational root with 2 complex. Of course, we know that's the case, so we know that's where we're headed. But those are the possibilities. Then to check out the negative rational roots, well, we're going to find f of negative x. So if I raise negative x to the 4th power, that doesn't change signs. If I raise negative x to the 3rd power, that stays negative x cubed, and that changes that 2 to positive. So 2x cubed. X squared, well, negative x, if I square negative x, that doesn't change anything, so positive. But that negative 18 turns to positive 18, and the negative 72 doesn't change. So then I'm seeing 0 sign changes, 0, 0. There's a sign change. So that tells me there's definitely 1 negative rational root. Of course, we know that. So what I've got to do is decide which one to use. And without looking back, I honestly don't remember what I used, so I'm going to have to play around with this. Maybe I'll cheat and go back and look. But let's, you try it. What we're trying to do, remember, is since I know there's only 1 negative, there is definitely 1 negative rational root, because I can't subtract 2 from that. We're going to use synthetic division to find that out. So I'm going to, because I'm such a good guesser, I'm going to try negative 2 in this polynomial. Let's see, negative 2, 1, negative 18, negative 72. So we'll bring down the 1, multiply. That's negative 4. We're going to multiply. That gives me positive 8, which is 9. That gives me negative 18, which is negative 36. Multiply, we get positive 72, we get 0. So negative 2 was the 1 negative factor. So now the other option was there was either going to be 2 positive rationals or 1 positive rationals. And I don't know. How about look at all that big long list, and if we cheat a little bit, look at what we originally said. What if we try positive 4 as our here? Now I'm going to line this up right here. What if we try positive 4 as a positive root? Well, that's going to be, bring down the 1, that's not going to be 4, which is 0, which is 0, which is 9, which is positive 36, which is 0, which gives me x squared plus 9. See how those factors are falling out of here nicely. And if we solve that, we're going to get x squared equals 9, negative 9. So that gives me x equals plus or minus 3i. And there's our 4 solutions. That's what the fundamental theorem of fundamental law of algebra tells us. If we wanted to write the factors, we would have to think about it as x plus 2, x minus 4, and then our x squared plus 9. Those would be the factors. And really that's back to where we started. So I hope all of this helps you learn how to put all this together and become good at factoring polynomials.